Everyone, welcome to the second page, and we're going to talk about linear approximations. And so very similar to linear approximation in Calc 1 and Calc 2, where we solved for y, know y is equal to, and then we had, our tangent, and we used our tangent line, and we had, m times x minus x sub 0, and then we had plus y sub 0 because we solved for y. And we use that to help do our linear approximations. Well, same thing with our tangent plane. Our tangent plane is going to help us solve and find our, and help us, approximate a value that's very, very close to the point on the surface that we're using. So in example 1, we found that an equation, the tangent plane to the graph of the function f of xy is equal to 3y squared minus 2x squared plus x at the point 2, negative 1, negative 3. And we found that to be z is equal to negative 7x minus 6y plus 5. Therefore, the linear function of two variables is going to be, cap L of xy is equal to, our tangent plane, negative 7x minus 6y plus 5. And it's a good approximation, to our function when xy is near 2, negative 1. The function L is called the linearization of f at 2, negative 1, and the approximation. So here, since it's approximation, we use the squiggle equals. And so this is called the linear approximation of the tangent plane approximation of f at 2, negative 1. So very similar to linear approximation, Calc 1, Calc 2. So let's go ahead and check. We're going to plug in 1.95 and negative 1.1 into our original function. So we're just plugging it into that function. And so we're going to check to see how good of approximation this is. So we have 3 times 1.1, negative 1.1 squared minus 2 times 1.95 squared plus 1.95. And when we do the math, we're going to get negative 2.025. Next, we have the linear approximation. Now we're going to use the linear approximation of the tangent plane to find 1.95, negative 1, 1. So we're using that. Negative 7 times 1.95 minus 6 times negative 1.1 plus 5. And doing the math, we get negative 2.05. So very, very close to what the function actually gives at that value. What you expect for a linear approximation. And let me go ahead and, because it's approximation, I know you should have put the squiggles there. All right. And so, in general, we know that an equation of the tangent plane to the graph of a function f of two variables at the point a, b, and f of a, b is. And so, here's our linearization. Here's the equation of a tangent plane. But instead of saying z minus z sub 0, we know that z sub 0 is just, whatever function we have plugging in a, b. And so, this right here just comes from the fact that z sub 0 is f of ab. So I don't want y'all to get confused with that. All right, and so here we just have z solved for, and we got rid of the z sub 0, and this is z sub 0. It's our initial z value. Then everything else follows the tangent plane. So it follows equation, what do we call that? Equation 2. All right, and so here we have our linear approximation, or it's also known as the tangent plane approximation. Now, what's next? We'll use this a little differently. I just don't. There's not really things that are going to be difficult for this part of the section. The only thing that I'm going to share with you, again, you can read this, is that delta z just means that your physical change in what either in y and z or in x. We're going to do an example showing you how to do delta z. So I don't want you to worry about it too much right now. And so next, we're just going to